Hello, year 6. Welcome to Natural Science lesson of today. We are starting correcting the exercises of the previous lesson. So exercise number 3, you've got here, because the Earth has a core of liquid iron that acts like a giant magnet. The magnetic poles are near the Earth's geographical poles. Some answers for the exercise number 4 that could be good are these ones. A paper clip can become magnetic for a few seconds because it is an induced magnet and only has a temporary magnetic force. B, the needle of a compass is magnetized. The end of the needle that points north is attracted to the Earth's magnetic North Pole. And C, letter C, explorers used dry compasses on ships because they were easier to use. And finally, the exercise number 5, we've got the letter A, which is false. There are several. Letter B, false, only temporarily magnetic. C, true. D, false, it is safe. And E, true. Okay, good. Now we continue with magnets and electromagnets. Good. Electromagnetism is the relationship between electricity and magnetism. Very important. Magnetism is created when electricity moves through magnetic metals. Okay, let's see how it works. So, first of all, we need metallic materials, okay? All magnetic materials are metallic. These include which kind of materials? Iron, nickel, cobalt, steel, and magnetite. If you don't understand the meaning of some of these words, remember you can go to word reference the dictionary, okay? Some metals are non-magnetic, including gold, silver, aluminium, copper, and titanium, okay? And non-metallic materials such as wood cannot be magnetic, never again, okay? Never ever. So they are not conductors, right? These are very good conductors, and these ones are not conductors, for example, wood. Many everyday objects have some parts that are magnetic and there are other parts that are not, okay? We can use a magnet to test these objects and their various parts. So for example, here we've got this pencil that we use every day. This part here, if you've got a similar model to this one, is magnetic material, okay? This battery too, and here that it's magnetic too. Okay, so electromagnets, let's see how they work. Electromagnets, it's a combination, okay, and are objects that act like magnets when an electrical current passes through them. So when electricity passes through the material, okay, the metallic material. They are not permanent magnets because they are activated by electricity. Okay, so these metals, these clips, for example, they are not metallic, but when we put them in contact with this battery, okay, in a closed circuit, very important, and the electricity passes in this circuit, okay, then they become electromagnet. But if not, and it's got a magnet influence here, and it acts like a magnetic metal. But if not, it doesn't have that property, okay? When we switch off the electrical current, the battery, the object loses its magnetism. We can create an electromagnet by coiling wire around a piece of magnetic metal, for example, this, or the objects and the materials that we said before, such as an iron bolt, and connecting it to a battery. The more coils of wire we use, the stronger the magnetic force will be. Okay? We can also use a more powerful source of energy to make the magnet stronger. Obviously, this battery will create stronger source, powerful, than this battery. Okay? Good. When we close the circuit, the object becomes an electromagnet. If we break the connection and open the circuit again, the object loses its magnetic force. Okay, interesting that. I want to show you now a video, okay? And in this video, first of all, I want you to listen to the first part where it explains what is magnetism in general, okay? Here we are.
Electromagnetism, or the electromagnetic force, is one of the four fundamental forces of nature. It generates light and energy and holds atoms, matter, and the world as we know it together. Electromagnetism is a branch of physics that studies the interactions between electric and magnetic fields. All matter has an electric charge, which can be positive, negative, or zero. Opposite charges attract, while like charges repel. These electric forces bring and hold atoms together. And when atoms gain a positive or negative charge through the transfer of electrons, a measurable electric field will form. If those electrically charged particles start to move, the field will become a flowing electric current and form a magnetic field around it. Under the right circumstances, interacting electric and magnetic fields can continuously produce and sustain one another. This generates an electromagnetic field that transmits waves of electromagnetic energy or radiation into space. The intensity of this radiation is determined by its frequency. These frequencies make up what's known as the electromagnetic spectrum. Near the middle of the spectrum is visible light, such as light emitted by stars, fireflies, and computer screens. On either side are invisible electromagnetic waves. On one end are long, low-frequency radio waves that broadcast television and radio signals, microwaves that carry telephone signals and cook food, and infrared waves emitted by fires. On the other are short, high-frequency wavelengths, ultraviolet, X, and gamma radiation. Unlike low-frequency waves, these waves can pass through the human body, making them useful for medical applications. While electromagnetism has daily applications, it's also the engine that drives the planet as a whole. Thousands of miles below the Earth's surface, a layer of liquid metals churn and flow. This generates electric currents that then produce magnetic fields that all together encompass the entire planet. Called a geodynamo, this process causes Earth's poles to attain positive and negative charges, turning the planet into a giant electromagnet. This phenomenon also creates a protective layer around the planet. It shields us from the most harmful radiation in space, leaving us to enjoy a world held together by the strange and fundamental force of electromagnetism.
Finally, magnets are everywhere. Magnets are part of our daily life. And if you look around or you think about different places where you've been to, you can see and find that there are a lot of magnets, okay? Look at home. Magnets hold notes on the refrigerator, and we have them in home appliances like blenders or motors have different ones. Healthcare in hospitals, we've got a magnetic resonance imaging where we go inside here. I don't know if you have experienced that. With that, what we can see is images of our internal organs. Okay, that's different from the X-rays where we can see our bones. But if the doctors need to see our organs more with more specific exactitude, we can see them. They can see them from there. Then transport. Yeah, they also use magnets. Several countries such as Japan and China have high-speed trains that are lifted above the ground. They are not touching. They haven't got contact, and that happens because they use magnets. Okay, this eliminates the friction of the train wheels, and that allows the train to travel faster. Okay, with that kind of levitation, you can also experience that kind of levitation with the attraction if you put the two poles of the magnets and you see that you cannot put them together. Okay, so yeah, even in the speakers they have magnets inside, which is very interesting, don't you think so? Right, homework, pages number 60, 76 and 77. You have to do exercises number 1 and 2 of the previous page, 76, and exercise number 3 of this page, okay? But Romina, number 3 has a listening and we cannot do it because we don't have the listening. Oh yes, you have it. Listen is very short and answer the questions.
A Danish scientist named Hans Ørsted discovered the phenomenon of electromagnetism in 1819. He observed that the needle on a magnetic compass moved when it was placed near a wire.
And that is all for today's lesson. Be good, do your exercises for next day, and see you soon. Bye bye. Take care.